Welcome back to our second day of sequences. This is day 15, writing general formulas of sequences. It's going to build directly off of day 14, and I think even in the past I've had these 2 days connected before, but it made a little bit more sense time-wise to split them. We've learned everything we really need to know about the types of sequences, recursive versus explicit in terms of formulas. What we're really going to do today is work backwards. So last class you went through and you had a formula, whether recursive or explicit. You plugged in values to find the first term, second term, so on and so forth. Today we are going to go the other way. You're going to have a sequence and you're going to write a recursive and or an explicit formula for it. So I'm going to do one of these for you and then let you guys think about the rest. I maybe will start with this center one right here and then have you try the opener. We are going to write 2 formulas for this sequence. We're actually going to focus on explicit today because those tend to be the more common and more useful formulas, but we are going to get some recursive practice too. Now, how do we write these formulas? Well, our recursive, and let's zoom in here, our recursive formula is going to look something like this. And in order to write the recursive, we probably need to figure out what the pattern is here. It looks like we are adding 3 each time, nothing too terrible. I think that's probably enough to actually write our formula then. We can say the general term, a sub n, to find the current term. We take a previous term. Imagine if we wanted to find 11. How do we find 11? We look to the previous term, and then we just add 3. We do want to give the starting point for the sequence, and the starting point for the sequence, the first term, is 2. So what this really means is start at 2 and add 3 over and over again until you get wherever you want to go. Now, in terms of explicit sequences, that one's a little bit trickier. I would say explicitly, you have a couple options. You can certainly write this in HK form, and that actually might be a little bit easier. But I'm also going to teach you a way to write it in MX plus B form because that tends to be a little shorter, a little more common. So let's look HK form first. So we're going to go ahead and again use that a sub n. And we're going to think HK form, right? Blank, x minus blank, plus blank. I think this first blank is probably the easiest. We need to realize that this sequence is changing by 3. Now, technically, a slope shows the correlation between how you change an input and what happens to the output. So what are the inputs for this sequence? So I'm going to quickly just draw a cute little table up here. What do we have? 4 of these? 1, 2, 3, 4. We have the outputs, the term values, if you will, and the inputs, which are the term numbers. So then maybe we can see that our slope goes up 3 for every 1 that we bump up the x. So I think our slope is definitely 3 here. Well then, in terms of HK form, what do we do for a point? Well, we have lots of points. We could use 1, 2, 2, 5, 3, 8, 4, 11. Traditionally with sequences, we use the first term, which is x minus 1 plus 2. And that would give us a perfect equation. And again, you could use another term number. You could say 2 and 5, that's totally okay. 3 and 8, whatever sounds good. But again, traditionally we see it written like this. And actually, even more traditionally, usually you see the order rearranged a little bit. But I'm going to keep HK form for the sake of simplicity here. Now, I also mentioned you could write this, and I'll do a little or down here. I also mentioned that you could write this in MX plus B form pretty easily. Well, we still know this is going to be 3. Oh, I'm sorry, I used x here. That was silly. N minus 1 instead of x. X isn't wrong. N is just usually associated with these sequences that have a domain of the natural numbers, and we differentiate that between using x, which would probably have all real numbers for our input. All right, mx plus b, 3n, nothing too bad, and then I'm just going to guess and say, okay, my sequence is 3n. Well, we're just going to quickly check that, and I'll give us some space up here. Is it 3n? Well, if I input 1 in for n, we know the answer, the first term, maybe you can see it up here, better be 2. So if I input 1, 3 times 1, I get an answer of 3. 3 is clearly not 2, which means I'm going to have to add or subtract something at the end to bring my answer back down to the correct one. So I think I probably, how do we get from 3 to 2? I think I need to subtract 1 here. And I think that will probably be our mx plus b, or our slope-intercept form for this sequence. However, once you do that, you always need to check another term. So let's check, I don't know, the fourth term. Why not? If I substitute 4 in here, 3 times 4 minus 1, 12 minus 1 is 11, and I do get 11. So that trick to writing your mx plus b form is really just getting the slope first, easy, you can see it in the pattern, and then just using this b value to adjust, to bump up or bump down the actual output. There are two other formulas here for you, two other sequences rather. If you could go ahead and write the recursive and the explicit for each one, that would be great, and then unpause me when you're ready. I am going to go through them, but you can skim that part if you can do it on your own. All right, at this point I'm going to assume that you have unpaused me. Let's look at these other two. Well, this first sequence, originally it seems like you add 2 and then add 6 and then, oh no, we're going up too quickly to be adding. I bet we're probably multiplying here. Looks to me like we're multiplying by 3 every time. And I think for a recursive, that's probably all we need in order to write this. That one's pretty not bad at all. We know the first term is 1. And to find a current term, we take a previous term and multiply it, well, by 3. Right? To get 9, we go to the previous term, do 3 times 3, and we're there. Cool. Explicits can be a little different. So for this explicit, I'm maybe going to suggest you think of this formula instead of 1, 3, 9, so on and so forth. What if you thought of this as 1, and then, well, how do we get to 3? Well, we take 1 and we multiply it by 3. How do you get to 9? Well, let's start back over at 1 again, and to get to 9, we do times 3 times 3. 27, start at 1. Always start at your starting point. It's going to make this a little easier. And then multiply by 3 times, and so on and so forth. Maybe from this pattern then, you can see that the general term for this sequence is going to be 1. There's a 1 that's in common every time. And then 3, but some number of 3's multiplying. In fact, an unknown, an n number of 3's multiplying. Then we just see, does this work? We might have to do that same thing we did on the previous one and modify this formula a bit. So let's see what happens for the first term. And again, we're going to take this 1 to be the first term here. So a sub 1 equals 1 times 3 to the first. That's just 3. Oh, that's not right. Okay. In fact, we're off by 1 term. This moved us to the next term. We actually, when we plugged in 1, we got the second term. And the way we move backwards in terms is we just take whatever term number we put in and subtract 1. And I think now we are going to get our right answer. A sub 1 equals 1 times 3 to the 1 minus 1. 1 times 3 to the 0th. 1 times 1 is 1. That looks pretty darn good. You can, of course, check this for any other one. Let's maybe check our third term. 1 times 3 to the 3 minus 1. 1 times 3 squared is 9, and 9 is our third term. Sometimes people ask, well, wait, couldn't we just assume that this is our 0th term, right? You said yesterday that a lot of computer science and computer programmers will use a 0th term, and you can. It's going to be a little bit easier to do that when we start working with series. So I'd say for today, let's assume that this is always the first term, and so we would need that minus 1 here for today. Let's go ahead and look at one more, which is this crazy one over here. This crazy one is a little bit trickier, isn't it now? We notice this one, it looks like, I don't know, are we adding 4, and then adding 6, and then adding 8? That looks pretty good. I think multiplying doesn't make sense, right? Times 3, times 2, times, no, the multiplication doesn't have a nice pattern. This one does, though. Add 4, then add 6, then add 8. Well, how do we do that recursively? This one gets a little bit more challenging here. Well, we can say that our first term is certainly 2. That's not bad. To find a current term, what do we have to do to the previous term? Well, that's a little bit trickier, isn't it? Now, there are a couple ways to come up with this. You can say, well, you might notice here, you're like, well, if you subtract these two, you get what you're adding, but that's not going to work because you don't know this term. How did we get to 12? Well, we went to the previous term and added itself. How did we get to 6? We went to the previous term and added 2 times itself. No, this one's pretty darn tricky. Explicitly, though, it actually comes out a little bit nicer. And maybe once we look at the explicit, we might be able to go back and do that recursive. So explicitly, I'm going to rewrite this problem slightly. And this just comes from having done a few of these to recognize this. I'm going to rewrite 2 as 1 times 2. And 6, I think, is 2 times 3. 12 is 3 times 4. 20 is 4 times 5, and so on and so forth. And now you can kind of see this pattern of numbers here, 1 and 2, 2 and 3, 3 and 4. And in particular, you might notice that the first number is actually the number term that's happening, right? Your first term is 2, your second term is 6, and the term number is just n in this case. So I think to maybe write this explicit formula here, I have 2 things that are multiplying. The first thing is just going to be n, right? That was the first of each one. That is our term number. Whatever number we plug in, that's the first number that multiplies. And then what do you notice about the second number? Well, the second number is always 1 larger than the term number. And look, we have a really nice formula right here. Now, recursively, do we have a nice way to do that? Well, think on it, and you might come up with a cool way. If you do, I'll leave this blank. I'll let you think about it, and you can always email me. There are many ways to do this. But for now, let's go ahead and jump further down. There are 3 very different patterns up above. We have our first pattern, which is multiplying by 3. Our second pattern, which is adding by 3. And then our last pattern, which doesn't seem to be doing anything constant, 4, 6, 8, anything like that. And these patterns and graphs all have names here. In particular, this first pattern where we're multiplying by 3, think of that maybe as a common ratio. And you might remember that something with a common ratio is known as a geometric pattern. But if you were to graph something like this, we would call the graph an exponential graph. Okay, and then mean, well, what do I mean? I literally mean the mean. The mean of this is that geometric is the mean. So what type of mean? Well, notice that if you have 1, 3, 9, 27, 81, if you wanted to find the geometric mean, well, the geometric mean is maybe something you haven't heard of before. The geometric mean is where you multiply 2 numbers together, and then you square root them. And the idea behind this is that we can take 2 numbers, and maybe we should use an example up here. Let's take 1 and 9. If I take 1 and 9 to be my a and b, I would do 1 times 9, which is 9, and then the square root of 9 is 3, and you'll notice that 3 is exactly in between 1 and 9, and that's not a coincidence. If I were to take the next 2 consecutives, skipping consecutives, if I were to multiply 3 times 27 and take that square root, that's the square root of 81, which is 9, and hey look, 9's right in the middle. So for any sort of exponential pattern, you can do this geometric mean, and it will always find the number in the middle of the 2 numbers that you did the geometric mean with. What is a geometric mean, in case you were curious? Well, imagine that you had, we'll just use the last ones I did in yellow, imagine you had a rectangle where the rectangle has one side of 3 and another side of 27. Well, what the geometric mean says is you can take those 2 sides and you can redraw that rectangle as a square. What size do the sides of the square have to be? Well, the way we do it is we'd find the area of the rectangle, 81, 3 times 27, and then we take the square root of 81, which is 9, right? This is a nice visualization of what the geometric mean means. Sounds silly to say. Okay, well, let's go ahead and look at our next one. The next pattern is where we added 3 every time. And when you add 3 every time, the pattern name for that is an arithmetic pattern. Now, arithmetic and arithmetic are 2 words like read and read. They do mean 2 different things. Arithmetic, if you do arithmetic, it's like you add, subtract, multiply, divide. Arithmetic is literally a pattern type. It's the pattern that describes something with a common first difference, right? You add 3 every time. Now, if you were to graph this, think about the graph up above. We already called it mx plus b. This graph would be linear. What is the mean here? Well, what's the meaning of the mean? Well, we can actually do an arithmetic mean instead of a geometric mean, and the arithmetic mean is the one that you're used to. So let's go ahead and just pull the 2 and the 8 that are up here. If we find the arithmetic mean, it's where we add them together and divide by the number of numbers there. So we end up with 10 divided by 2, which is 5, and you'll notice that 5 is in between those two numbers. Okay, that's what always happens for an arithmetic sequence. And now we come to our last pattern. And this was that weird one, 2, 6, 12, 20. And I suggested rewriting it like so. And this is actually going to give us a deeper meaning when we get to the picture part down below as well. So stay tuned for that. Well, you might have recognized based on the formula up above, if you multiply everything out, that it becomes n squared plus 1n. So you might recognize that as a quadratic equation, right? X to the second power. And what type of graph do quadratics make? Well, they of course make parabolas. We should know that by now. But what about this picture? Notice I'm not doing a mean here. We're not going to do a quadratic mean. But instead what we are going to do is interpret this pattern in terms of pictures. And in particular, we're going to interpret this as a length and a width of a rectangle. This rectangle is going to be a 1 by 2. Right? 1 high, 2 across. Or you could, of course, go the other way. If I wanted to interpret 6, we would say 2 across by 3 high. Okay, if I want to interpret 20, I'm going to need more dots here. This would be like 3 across and 4 tall. And then, of course, we could fill in the rest of these. And then if I wanted to do my next one, well, I'm not even going to do the number, just follow the pattern. This one's going to be 4 across and 5 tall, and it's going to be something like this. Okay, and I guess I am 1 off. This really should have been 12, shouldn't it? Whoopsies. And then we get 20, and so on and so forth. It's very easy to extend that pattern, right? We just go 1 further, and then we have to fill in the rest of the dots like so. And this is our quadratic pattern. And it's going to work that way every single time, which is, I think, pretty cool. Sometimes it'll be like something -1, and you might lose the corner of it every time, but either way. So that would be our same quadratic formula, just with a -1 at the end. But it's still that same pattern. You might just have some gaps. Okay, now we just took some time to go through one example of each of these. However, we're going to do a bit of a deeper dive into each type of sequence, because your goal by the end of this is to be proficient with writing explicit formulas, or general formulas, general terms, for each one of these. Because although recursive formulas are pretty fun, they're much less commonly used, and the reason why is because they recall or they call on previous terms to get a current term, and that tends to be a little tedious. If you want the 15th term, and to get that you need to first look up the 14th and the 13th and the 12th and so on and so forth. So here we go. Exponential or geometric sequences have a common ratio. We are going to write the general term for each sequence below, and then we're also going to go ahead and find that common ratio. I think it's good practice for us. So I'll do one of them just to show you what I'm looking for, and then you guys can try the rest. So when we talk about a common ratio, we're really discussing two consecutive terms, one divided by the other. So my common ratio here, and I'll maybe do the work over on the side, is going to be find two consecutive terms. Well, here's two consecutive terms. Here are two consecutive terms. I'll just take these last two, why not? And the ratio, sometimes you'll see it written 16 to 8, other times 16 divided by 8, other times 8 divided by 16. Usually we do the second one over the first one, right? Sometimes you'll see this common ratio as a sub n plus 1 over a sub n, the current term, and then the next term on top. And regardless, though, you're going to get 2. And you'll notice you get that every time. 8 divided by 4 is 2. 4 divided by 2 is 2. Another way to think about that common ratio, if you do it this way, is what do you have to multiply by each time? Well, we have to multiply by 2. This is known as our common ratio. Ratio, fraction, anything like that. Now, when we write our formula, I think we're going to incorporate that common ratio. We're going to say a sub n. And then I really like that visual I showed you before where I wrote it as 1. And then 2 is going to be 1 times 2. And then 4 is going to be 1 times 2 times 2. 8 is 1, and then 3 of those 2's, and so on and so forth. I think that really gives you a nice visual of what's happening here. We start at 1, and then we multiply by 2 n number of times. However, if you replace n with 1, you're not going to get 1. If you replace n with 1, you get 2, so that's one term too far. We need to subtract 1. Why don't you guys go ahead, take some time, work through these 5 other problems. You'll notice that there's a slight difference in every single one of these problems. That's done on purpose. There's some very, very similar ones, but go through, find the ratio, and then once you're ready for that, once you've written the formulas, get back to me and we'll see how you did. Okay, so hopefully you've gone through and done everything here. I'm just going to quickly go through this. You are definitely welcome to skim, maybe play it at 3 times speed on mute just to see if you did it well, or listen through to my fun voice. This is actually my maiden voyage of my new headset, so hopefully the microphone sounds a little snappier. We'll see. Maybe it'll be too snappy. So, common ratio. With our common ratio, we just picked 2 of them. 32 divided by 16, that's 2. Of course, we probably could have seen that just by realizing we have to multiply by 2 every time. Very exciting. And then a sub n, well, if I rewrite this formula, I started at 2, and then 4 is 2 times 2, and then 8 is 2 times 2 times 2, and 16 has 3 2's after it, and so on and so forth. We could write this as 2 times 2 to the nth. You'll notice that'll be 1 off, so we have to subtract 1. Of course, you also might notice that because these have the same base, we can add the exponents together, 2 to the 1 plus n minus 1, but then your 1's cancel, and we really just get 2 to the nth. That might have been even easier if you recognize that. Now if you replace n with 1, you get the first term. N with 2, you get the second one. Exciting, you rock. Let's scoot on. Our third one over here, I think, again, has a common ratio of 2. Very creative, Mr. Grant. So our common ratio is 2, looking nice. And then our a sub n. Well, again, I still like to rewrite it like so. It's 1/2, and then it's going to be 1/2 times the common ratio. 1/2 times the common ratio twice, and 3 times, and so on and so forth. So let's see if we get it. Is it 1/2 times 2 to the nth? Well, if n is 1, that again brings us 1 too far. I think that's got to be an n minus 1. Now, you could again be very creative here and take a look. 1/2, that's 2 to the negative first, isn't it? Don't know why I put an equals in between. I think 2 to the negative first is equivalent to 1/2. Add these exponents again together, and we get 2 to the n minus 2. And if you put 1 in here, 1 minus 2 gives you 1/2, and you get the exact same answer. Let's look at a few more. Common ratio. Whew, this one looks a little trickier. Let's take the 1/8 and divide it by 1/4. So I think maybe we'll multiply both of these by 4 over 1. That's where your skip flip multiply comes from, by the way, right? And we get 4/8. So it looks like our common ratio is 1/2. To check, do we multiply by 1/2 every time? Half of 1 is a half. Half of a half is a quarter. Yeah, we're looking pretty awesome. So we continue on through. A sub n equals, I should have written this over here. It's okay. We're starting at 1. The next one is going to be 1 times a half. Next one is 1 times a couple of those halves, and so on and so forth. I think we're looking at 1 as a starting point, and then multiply by n number of 1/2, and you're probably used to it now with that minus 1. Well, can we do anything else with this? You bet we can. You might realize we don't need the 1 there. So what if I rewrote again the 1/2 as 2 to the negative first? And then we could remember that we're allowed to distribute this exponent, so to the negative n plus 1. Another way to write this. All of them are fine, though. Here comes our fifth. I think we can skip the common ratio and tell that this is probably 1/2, right? We always work from left to right, so we're multiplying by a half. We usually don't say dividing by 2. You can divide by 2, and there are ways to write a formula that way, but I think that this will look a little bit nicer and more in line with what we've been doing. So we started at 64, and then we did 64 times one of those 1/2, and then we did 64 times a half times another half, and so on and so forth. So 64 times 1/2 to the n minus 1. And that's looking pretty nice, but I bet you didn't expect this, or maybe you did. I think we can rewrite 64 as 2 to some power, can't we? Let's see, 2 times 2 is 4, a third 2 is 8, fourth 2 is 16, fifth 2 32, sixth 2 I think gets us 64. And then 1/2 is 2 to the negative first to the n minus 1, or 2 to the sixth times 2 to the negative n plus 1, same base, 2 to the negative n plus 7. Pretty crazy there, right? Now if you plug in 1, 7 minus 1 is 6, 2 to the 6th is 64. If you plug in 2, 7 minus 2 is 5, 2 to the 5th is 32, and so on, so forth. So just a different way to look at it. And then let's go ahead and take a peek at our last one. This one looks pretty much the same, except we're multiplying, by I think negative 1/2 this time, aren't we? Times a negative 1/2 every time. So if we wanted to rewrite this, we start at 64, then my next one's going to be 64 times a negative 1/2, and then the next one 64 times a couple of those, and so on and so forth. So it looks like an easy way to write this formula is start at 64 and multiply by negative 1/2 and minus 1 times. Do you think we're going to rewrite it? You know it. So let's take a look here. 64 we already said was 2 to the 6th. Negative 1/2 is an interesting one. So we can definitely write this as negative and then 2, right, to the negative first, and then all of this to the n minus 1. What I'm going to do, though, is kind of a cool little trick here. And that cool little trick involves introducing an extra negative 1. So what we can do, well, let's clean this up a little bit first. So we're going to get 2 to the 6th times negative 2 to the power of negative n plus 1. And then we might realize that, I'm going to run out of room here. That's definitely what we're going to realize. We get 2 to the 6th times, what if I did this as negative 1 times 2 to the negative n plus 1? I think that's the same thing, isn't it? And then we also might realize, and for example, it's easy to see if I did 2 times 3 to the second power. Well, that's 2 times 3 times 2 times 3, which rearranging is 2 squared times 3 squared. Notice we can actually distribute this square or any power as long as we just have multiplication in the middle. So if I went through and distributed here, I think we end up with 2 to the 6th times negative 1 to the negative n plus 1 times 2 to the negative n plus 1. Well, why did I do that? Because now I have two terms that have the same base, and I'll leave that negative 1 to the negative n plus 1 out front. Same base, add the exponents. It's going to be 2 to the negative n plus 7. Now, this won't shock you too much because look at what we got over here. They are almost exactly the same. We just had to put this little negative 1 to the negative n plus 1 out front because, and we saw this before, last class, negative 1 to the n, negative 1 to the n plus 1, anything looking like that plus 1 is going to cause our sequence to alternate in sign. Now, you might be saying, whoa, 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 whoa. Why did you even do all of that? Well, the reason that I cleaned all of these up is to show you that all of these can be rewritten as an exponential function that has a base of 2. But notice, not all of them started off with a base of 2. We had a base of, and I'll use a different color, 1/2 here. This one had a base of 2 at the beginning. This one wasn't too bad. This one also had a base of 2. We had some bases of 2, but then we had multiple terms. And you'll notice that we were able to combine all those multiple terms together and come out with a base of 2. So why did I want you to do it? Because it's good practice, right? You should go through and be able to manipulate these. Do you have to? No. But we are going to be using a lot of properties of exponents, so it is good practice to see those different properties in action. Okay, well, what's next? Next up, I think we have our linear or arithmetic sequences. And these have what's called a common first difference. Sometimes people just say a common difference, same idea. We're going to talk about that first difference later on, though, so why not? And then it asks you to write a formula for this using a whole bunch of different terms. Well, remember, then I'll rewrite this sequence up above. First term, second term, third, fourth, fifth, third, fourth, fifth. Okay, something like this. My first term is 5, second term is 1, -3, -7, -11. Well, if I'm going to write a formula for this and they're asking us to use different terms, then I think HK form is going to be the way to go. A sub n equals, well, I guess I need my slope. It looks like we're subtracting 4 every time here. So A sub n equals -4, x minus 1, the first term, plus 5. Great, it's pretty easy. Writing the formula using the second term, -4, x minus 2, plus 1. Third term, a sub n, -4, x plus, nope, -4, x minus 4, third term, Mr. Grant, x minus 3 minus 3, there we go. Fourth term, -4, x minus 4 minus 7. Well then, what about slope-intercept form? Slope-intercept form, I showed you that trick before, isn't too bad. We're going to say it's -4x, that's the slope, and then see if we're right. So to see if we're right, we're going to take 1, substitute it in. -4 times 1 is -4. Is -4 the same as 5? Well, certainly not. What do we have to do to -4 to bring it all the way up to 5? I think we have to add 9, don't we? So my guess is my slope-intercept form is -4x plus 9. Let's check with another term. Let's check with 2. If I evaluate 2 in here, -4 times 2, that's -8 plus 9, that is +1. Nice, I think that is my slope-intercept form. I again should have used n, still stuck in my weird x ways, and it looks like I did that every single time. Again, you're not going to lose points there, but we should try to match variables, and n is almost always the variable used for these sequences. Last but not least, the 0th term. I think that just involves us moving backwards in the table over here, and we probably have to work with this formula. We'd have to add 4 to move to the left. 4 plus 5 is 9. So I think this would be -4 times n minus 0 plus 9. But isn't that just the same as slope-intercept form, right? Slope-intercept form, you could always put a -0 in here. It doesn't change anything. Yeah, 0th term and slope-intercept form are exactly the same. The only thing we needed to experiment here was just the difference between HK form of different terms and how we can write slope-intercept form. And full disclosure, although I usually am a fan of HK form, I actually tend to write sequences in slope-intercept form. I think it's just a little quicker because you always know you're starting at the first term. All right, last but not least. Quadratic sequences also have a common difference, but unlike this one, which had a common first difference, which means at the first level there was something common happening to each of the terms, these ones have a common second difference. Okay, and this should make sense because linears and quadratics are types of polynomials. Okay, so they actually have a common difference built into their pattern. Now, what do I mean by that? Well, looking at this pattern right here, this is going to be quadratic. All of these are. Let's look at the pattern. We increase by 3, increase by 5, increase by 7. There's nothing common, but this is like our first level of differences. What happens to the differences of the differences? Well, we go up by 2 to get from 3 to 5, go up by 2. I think this is going to be common. In fact, if we go 3, 5, 7, we go up by 9. Yeah, you'll notice that there is a common second difference. And it's not because this number is at 2, it's because we're on the first, no, second level here. Now, this shouldn't shock you knowing what you know about derivatives, but let's prove that to us first. So let's go ahead and rewrite this sequence like so. It's always going to be two things multiplying. These quadratics make rectangles. My first one is 1 times 1, 4 is 2 times 2, 3 times 3, 4 times 4, and so on and so forth, right? And then let's go ahead and write that formula. So our general term, well, 1 is n, that's our first term. Second term, third term, fourth term, I think we can just say it's n times n. Or, of course, n squared. And then we check it. If we substitute 3 in here, do I get the third term? Well, sure, 3 squared is 9. Well, I mentioned something about that common second difference not being a surprise. Let's maybe compare this to the function f of x equals x squared. That's continuous, right, for all numbers. We can take derivatives. We're still not sure if we can take derivatives of sequences because they have individual terms. They don't really have slopes because they're discrete as they go through. But I know I can take the derivative of x squared, and I think that'll illustrate our example here. The first derivative is 2x. There's a variable here, so the value of the first derivative is going to vary. It's not going to be the same. However, the second derivative is constant. And the second derivative tells us what the first derivative is changing by. So that is why our quadratics have a common second difference. Right? If we had some sort of cubic function, and let's just do an easy cubic function, I'm just going to cube every input. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, so on and so forth. As you look at their common differences, you're not going to see much here, right? We go up by 7. This one we go up by 19. That's pretty gross. And then this one, quick math, it looks like we go up by 37, and so on and so forth. But then if we look at the second common difference, we go up by 12. And then this one, I think we're going up by 16. My guess is we're going up by 4s here. I bet this next one's going to go up by 20. And then take a look at my third common difference by 4, and so on and so forth. Or actually, it may even go up by more than that, which is fine. Just double checking. Oh, there's my mistake. I was like, whoa, it shouldn't be a common 4. This should be 18. Sorry. Math apparently is hard. It went up by 6, and then 18 and 6 more is going to be 24. So this increases by 6. And the reason that I knew it went up by 6 is I was envisioning f of x equals x cubed and just doing some quick derivatives, right? This becomes 3x squared, nothing constant. Second derivative is 6x, nothing constant. Third derivative, though, is 6. So that means we had to have been changing by 6 every time. Whew, that was a lot of explanation. Okay, well, there are a couple more here that we should probably go through, and you can definitely do this on your own, not a big deal. What does this next one look like? I always have to rewrite these first. 4 is, of course, 2 times 2. 9 is 3 times 3. Oh, we just did something super similar to this. 5 times 5. What does our formula look like then? Well, this is supposed to be my first term, and each of these 2's are 1 bigger than the first term. This is my second term. Each of these are 1 bigger than 2, and so on and so forth. So I think it's not going to be n times n, because it's not the first 1 times 1. It's 1 bigger than the first term, and 1 bigger than the first term. If we substitute in 1, we get 2 times 2, which of course gives us 4. Looks pretty good. Nothing too terrible. If you wanted, you could also try to build some rectangles here, right? If we built a rectangle for 4, we saw that that's a 2 by 2 rectangle. Fill in the gap. 1 for 9, that is a 3 by 3 rectangle, and then fill in the gaps. We're just going 1 larger in every direction. So if I built this next rectangle to be the next one, I need to go 1 higher and 1 more out, and we end up with our next one, which is 16. All right, rectangle patterns work. Awesome. Let's look at a few more. Okay, can I rewrite this one? I think so. I think this is probably 0 times 1, 1 times 2, 2 times 3, 3 times 4. Nothing awful here. And then in terms of a formula, it looks like n is the second one of these. So it's going to be something times n. Well, how does the first digit of this factor, I guess, relate to n? It's 1 smaller, so I think it's going to be n minus 1. The rectangles here aren't going to be anything weird, so we're not going to draw those. And let's get to our last one. This last one I think could be much more interesting. Right, 3, 8, 15, 24. Ugh. Well, always bring it back to 2 numbers multiplying. And you actually might notice that these are, if you add 1 to each of these, that they become perfect squares. So to me, it looks like we're doing basically 2 squared minus 1, 3 squared minus 1, 4 squared minus 1, and so on and so forth. Or another way to visualize that is we're doing 2 times 2 minus 1. 3 times 3 minus 1, 4 times 4 minus 1, and so on and so forth. So I think that's going to give rise to the general term of n. Oh wait, 2, let's see, this is our first term, isn't it? This is n equals 1. So these 2's are 1 bigger. So I think it's going to be n plus 1 times n plus 1 minus 1. Right? If we try an n of 1, we get 2 times 2 is 4, minus 1 is 3. Yeah, that looks pretty good. Can we draw rectangles for this one? This one might be pretty cool. So it looks like our first rectangle, or square in this case, is going to be 4. It's going to be 2 by 2. However, it says build that rectangle, but then take 1 away. And for whatever reason, I always start with the upper right. Nothing too weird. 3 times 3 is going to be a 3 by 3 square. Oof, dot is gross. But then it says get 1 smaller than that, so we're going to remove 1. And we can still see the pattern. It is still quadratic. It's just kind of like something's eating a bite out of our square or our rectangle. Well, now that we know those 3 main patterns and we've practiced looking at patterns and writing explicit formulas, let's look at some ones that don't fit really any of those patterns. There are, I think, 8 of these left. Why don't you guys go ahead and try them on your own? Try each one, and then once you've tried them all, maybe you're successful in all of them, you can come back and listen to me take you through them. However, if you weren't successful, you can skip to the ones you weren't successful on, whatever sounds good to you. Okay, hopefully you've tried all of these. Let's go ahead and see what I'm going to do with them. Well, this one doesn't seem too bad. I think it's really just going to be 5, because it's 5 every single time. However, it's alternating in sign. And whenever something's alternating in sign, I always like to give it that -1 to the nth. And then we'll see if we're right. Well, if n equals 1, that's going to be -1 to the first times 5, which is just going to be -5. But my first term's not negative. Do I have to do everything over? No, it's really easy. We just put a little +1 right there. Nothing bad. And then we try again. Okay, so if I wanted to find a sub 1, it's -1 to the 1 plus 1 times 5, -1 squared times 5, a -1 squared is +1. There we go. And if you wanted, you could try 2 in there. All you're going to see is the same thing as before. This is just going to be a -1 now, right? -1 to the third, which gives us -5. Nice. Now, this formula over here hopefully isn't too scary that I can do really quickly because it's the same formula. Yeah, we just had to go through and put an n instead of n plus 1. Uh-oh, tricky ones. Fractions. How dare I give you weird fractions? Actually, fractions are really easy. Don't even think of them as fractions. Think of them as 2 different patterns separated by that fraction line. And so here's what I'm going to look at. I'm going to say that a sub n equals, oops, slow color change, equals, and then I'm going to do a fraction and literally treat them as 2 completely separate patterns. So let's look at my first pattern first. 1, 2, 3, 4. This is a linear pattern, or it's the combination to my luggage, and it looks like it's going up by 1 every time. If it's linear, I know that's going to be 1n. That's my slope of 1, and then we'll see, am I right? Well, the first term means I plug 1 in here. 1 times 1 is 1. Yeah, that worked out. Second term, if I plug 2 in here, 2 times 1 is 2. That worked out too. Cool. That's awesome. I found the pattern for the top. Now let's do the same thing for the denominators. What's my slope? I go up by 1 every time. Nothing bad. So that means my slope has to be 1n. And then we try the first term. The first term better get us an answer of 2. If I substitute 1 in here, though 1 times 1 is 1, that's not 2. What do I have to do to 1 to make it into 2? I need to make it 1 larger. And then we should always check one more just to make sure. This is my second term. 2 times 1 is 2, plus 1 more does get us to the 3. Great, there's my formula for that sequence. Again, 2 completely independent patterns. The numerator and denominator aren't related to each other at all. So let's look at one more. I think if we look at this pattern, things are getting nothing too crazy. We can go through, do the same trick. Look at the numerator. The slope is again up 1, so we know it's going to be 1n. This has to be my first term though, and when I plug 1 in here, I don't get 3. I just get 1, so I think we need to add 2 more. But we should probably check n equals 2. Substitute in 2. 2 times 1 is 2. 2 plus 2, 4. Yeah, okay, that's looking pretty good for the numerator. What about that denominator? Denominator, my slope goes up 2 every time, so that's got to be a 2n. And then we see, are we right? Well, when n equals 1, I better get 5. But when I substitute 1 in here, 2 times 1 is 2, we need to add 3 more to get to 5. Trying n equals 2 to make sure we're right. 2 times 2 is 4, plus 3 more gets us 7. Now, could you have written all these in HK form? Absolutely. There's nothing wrong with writing them in HK form, right? If you wanted to see this in HK form with, say, the first terms on each of them, then this would be 1 times n minus the first term plus 3. And then the denominator, which is this part down here, would be 2 times n minus the first term, which is 5. You can multiply all of that out and see that it's the exact same, and you're totally welcome to write it like that. Much more common to see it this way, though, so it's nice to practice something different since I've really, I hopefully converted you into HK form for the last year and a half. We don't want to forget that there are other forms, too. Let's look at this one down here. I'm going to go ahead and take these cute little negatives and move them up here just so we can have two distinct patterns, where one pattern is going to be -1, +1, -1, +1. And I think that's just our alternating factor, -1 to the nth. If I substitute n equals 1 in here, we do get a negative, which is what I'm looking for, so that looks pretty good. Denominator-wise, let's see the pattern. It looks like we're multiplying by 2 every time. Multiply by 2, oh, that's got to be our exponential. So I always rewrite these exponentials and I say we started at 2, and then we took 2 and multiplied by the common ratio, and then we can start at 2 again and multiply by the common ratio twice, so on and so forth. Maybe we can see that this is just, let's just start with 2 to the n and see if we're right. If we replace n with 1, we do get 2. We replace n with 2, we also get that. Now notice you could have written this as 2 times 2 to the n minus 1, but then it's 2 times, and then how do we, well, this is to the first, so we just add those together, I think, right? And when you add them together, you get 2 to the n. Okay, moving on, 3 to go. 1, 2, 6, 24, 120. Huh, well, that's weird. We haven't seen one of these before, so let's try maybe thinking about, if we add 1, 4, no, that's going to be weird. If we multiply times 2, times 3, times 4, times 5, well, that's really strange. With our exponentials, we multiplied by the same number every time. In this one, we're multiplying by a different number. How do we show that? Well, maybe let's do that same trick for exponentials, and let's start at 1 and see what happens. Start at 1, cool. How do we get to 2? Well, we take 1 and multiply by 2. How do we get to 6? Well, we take 1, we had to multiply by 2, and then you have to multiply by 3. How do we get to 24? Well, we have to start at 1, we multiply by 2 to get us to 2, by 3 to get us to 6, by 4 to get us to 24. Do we see what's happening here? Oh yeah, these are factorials. And I think then that my answer is just going to be n factorial. Told you it was going to come back. You're going to see a factorial almost every day. Very, very commonly used in our sequences and series. They have a lot of applications for us. 2 to go. 1, 1, 2, 6, 24. Huh. Well, we know these are factorials, so let's just see if that works. 7 equals n factorial. Let's try a few of these. For a sub 1, that would be 1 factorial, which is 1. That worked out really well. Cool. For a sub 2, that would be 2 factorial. 2 times 1, that's 2. Uh-oh, my second term's 1. Well, why would there be an extra 1 there? Oh, maybe we remember that 0 factorial is 1. 1 factorial is 1, and then we have 2 factorial, 3 factorial. That's 0 factorial rearing its ugly head. So when I plug a value in here, when I plug 1 in here, I want it to turn into a 0. And the way that we do that is we just bump our factorial back by 1. And I think this will be just fine. Okay? Now, let's go ahead and look at our last one, and hopefully my computer survives. My battery light just came on because I forgot to plug it in. So here we go. For this last one, what's going on here? I don't see these all as fractions. I think I want to do that. 2 over 1, 3 over 2, 2 over 3. I feel like with this pattern, 1, 2, 2, 3. Oh, wait, this is weird too. Okay, let's just keep it as is. 5 over 24 and 1 over 20. Well, I don't see any common denominators here. That's kind of strange. One thing I am noticing though is this 1, 2, and 24 pattern. Didn't we see that just before with factorials? What if I just messed with these last two denominators here? So I said it was something like this. I like this 2 over 1. I'm okay with 3 over 2, but let's make this denominator a 6. The reason I'm making it a 6 by multiplying top and bottom by 2 is because then that fits our factorial pattern. 5 over 24, and then let's multiply this one. Let's see, 20, I think 120, so times 6 here. 6 over 120. And then, oh, look at that beautiful pattern. Isn't that nice? I think our denominator isn't going to be too bad. Our denominator is probably just n factorial, right? When we look at that pattern. What about the numerator? The numerator is increasing by 1 plus 1 every time, so it's 1n. If I try n equals 1, I need to get 2, so I think we need to add 1 more. And we have our final general term. You don't have any independent practice today. I think we got plenty of that on here, but come prepared with these talents for next class.